Hi dear students, welcome to our YouTube channel Math Universe with Dr. Naseer Ahmed. Dear students, this video I am recording on Matrices Kcet for Common Entrance Test from Karnataka. See, already part 1 I have uploaded, but then I got a thought that let I just give a small video on concepts of PUC, because there I said that concept I'm not going to discuss again because it is already there in NCRT. I think about PUC, the which I think around 3 videos I uploaded with respect to model question paper. No, it was said 70% of the question will come from those 3 model papers. There I give detailed concept for all the chapters. I give the detailed concept. So I was of a thought that let you refer there, but maybe due to time constraint you may not be able to do so. So that's the reason for all the chapters I will try to just give the synopsis. Okay, so detailedly let's try to have a synopsis, and then we will take the problems. So for this chapter matrices, this will be taken as part 1, and the one which is already uploaded, that will be part 2, and the remaining problem which is left out, for that it is part 3. Okay, so 3 parts we are going to have in matrices. So this one we can regard as part 1. So here only synopsis will be discussed. So let us recall what is a matrix. Matrix is an rectangular arrangement of numbers or elements or functions enclosed by a rectangle bracket or a small bracket. Now if I just write here 1, minus 2, 3, then 7, 0 and sign x, and all the matrices are denoted by capital letters A to Z, whereas the elements which are written here are written in small letters A, D, 0, L. Now either it can be a small bracket or a rectangle bracket. Now comes order of a matrix. What is order of a matrix? Order of a matrix is going to give an idea about how many rows and columns do we have. What is a row? Horizontal arrangement. This we call row. How many rows we have at 2? Here also how many rows we have at 1, 2. So this we call row. And vertical column, this is a vertical line and this is a column. Column number 1, column number 2 and column number 3. So 2 cross 3 is the matrix order. And here column number 1, column number 2. So 2 by 2 is the order of the matrix. So order of the matrix, assume you know, let's suppose m cross n, always m will be number of rows and n will be number of columns. As soon we know the order, then the number of elements is given by product of the order. And as you can see, 2 3s are 6. Just count 1 2 3 4 5 6. Just 6 elements we have. Again 2 2s are 4. Yeah, 4 elements we have. Okay, now comes now general representation of any matrix. See, as you can see here also, what is the location of 1? It is there in first row and first column. So this is A11. This is there in which row? First row and third column. So A13. So the general way of writing any matrix will be A is equal to small a11, a12, a13, like this, a1 jth column, and lastly a1 n column. Similarly, coming to second row, a21, a22, a23, a2j, a2n, like this. Ith row, ai1, ai2, ai3, aij, ain. That's the ith row. Now the last row, mth row, am1, then this is am2, am3, amj column, and amn. So what this general representation is saying and what this index is saying, for example, this element says, hi, I am the element A23 present in second row and third column. Always the first index is going to talk about row, second index will be talking about column. As a convention, you can remember. It's a rule. Okay. Same like now when you are going on the road, if you're just going like this, this we call right, this we call left, right? Why it is so? Okay, with respect to me, it is now right. Or if you talk with respect to you, for you it is left. No, for you also it's right only. Yeah, correct, correct. For you also right, because when I'm seeing the camera, right, this is right and this is left. Okay, now with respect to whatever I'm showing them. Why are we calling this as right? Why we can't call this as left? And why should we call this as a straight? If we are not going to have a uniformity when we are on the road, going to office, going to school, college, and if you have no different this direction, I say straight, but someone say it's right, someone say it is left. There's a confusion, chance of accident, right? That's the reason we have got one universal target. This is right, this dash is left, this is straight. Similarly, coming to matrix, always the first index is row, second is what? Column. Convention throughout the world, because exchange of knowledge is also going to happen. It's not within Karnataka or within India. Throughout the world, this knowledge is going to be there. And when you want to communicate with them, since it's a common way we are going to have, a universal way we are going to have, a convention we are going to have, we can always collaborate with them. Okay? I'm talking about research. So anyway, so this will be the order m by n. So m by n, the order is given by the last row. See, m, and here n columns. So you can see here now, here the location of this is what? Second or third column, 2, 3. This is second or second column. Fine. So in place of already such a big matrix, we have a small one, small a I j, m by n, where I is running from where to where. See, I is the row, first row, second row, up to ith row and mth row. So 1 less or equal to I, less or equal to m. Coming to j is first of column. So first column, second column, third column, jth column, and last nth column. 1 is less or equal to j, less or equal to m. This is going to happen for all I comma j belonging to natural number. M and n is also a natural number. Okay. I hope this is clear. So in place of such a big matrix, we had a small matrix. This is about the representation. Now let us take a types of matrices. Kindly make a note. And this is the general representation of a matrix. And I would suggest to all the students that as and how I am giving the concept, kindly make a note, especially the properties. In matrices and determinants especially, properties will be served as a shortcut for us. Okay, and not only for this chapter, as and how I give the synopsis, try to know when you're attending the class, at least leave some 3 to 4 pages empty after writing the chapter name. And as and how I'm giving the properties, list out these properties in those pages so that you are aware these are the properties to be learned by you, to be memorized by you. Okay, fine. Let's move on to next. Now, dear students, let us move on to the next topic, that is types of matrices. I feel the ink is bit, it's not bright, so let's fill the ink. So moving on to types of matrices. The first matrix is a column matrix. Understand, matrix is singular, matrices is a plural. Okay, so as we just discussed, that for any general matrix, the order is m by n. So where m stands for number of rows and n stands for number of columns. So let I have that one here. So a is equal to small a I j, okay, of order m by n. Now where m stands for, as we know, number of rows and n stand for number of columns. So coming to a column matrix, any matrix whose number of columns are 1. So since n stands for columns, so if I talk about in general, A is equal to small a I-j, the order will be m cross 1, nothing but always number of columns will be 1. We are least bothered about number of rows. It can be 1 or it can be any number, but finite. Okay, next, finite number of rows should be there. Coming to any matrix, number of rows and columns should be finite. Okay, next, one example on this will be A is equal to -2, 3, and another was sin x. Purposefully, I'm bringing trigonometric function repeatedly or other functions so that you are getting used to it. That it's not only numbers, it can be any function as well. So here, how many rows we have got? 1, 2, 3. So 3 rows and only 1 column. Hope so it's recording. Yeah. Next, moving on to, so this one we are going to keep, okay, as a reference. Now moving on to the next one, it is about a row matrix. What is a row matrix? Any matrix in which number of rows are 1. For example, B is equal to Bij. Okay, and since the order is m cross n, m stands for number of rows, and number of rows should be only 1, and any number of columns. So here m number of rows is 1. One example can be B is equal to log x e power minus x. Enough. How many rows? Only 1 rows. How many columns? 1, 2, 2 columns. Okay, this we call row matrix. Next comes, see, before I go to square matrix, now purposefully I want to take as a type 3 rectangular matrix so that you are aware about what do you mean by square matrix, and if it is not a square matrix, what type of matrix it is. Rectangular matrix is a matrix in which number of rows and columns should not be equal. For example, if I take C is equal to Cij m cross n, when I use the two different letters now, it means they may be same, they may not be equal. Now here I am very explicitly writing that number of rows and columns should never be equal. Only then we say it's a rectangular matrix. Rectangular matrix. For example, let us suppose I will have some matrix C is equal to 1, -2, 3, root 2, 5, and here let us suppose log 2. So how many rows do we have? 1 row, 2 rows. 2 rows we have. And how many columns we have? 1 column, 2nd column, 3rd column. So this will be our rectangular. So you can see number of rows and columns are different. Now here one doubt will come, sir, can we say every column matrix and row matrix will be rectangular matrix? Wait for it. Wait for it. Let us not comment so early. Okay. Now moving on to the next is square matrix. What is a square matrix? Now see, having defined what is rectangular matrix, now it becomes a bit easier to comment about square matrix. Any matrix in which number of rows and columns are same. So I'm just trying to use all the alphabet. Okay. So as I use capital D, I'm writing small element Dij, as we know that all the elements inside the matrix should be in small letters if you are using some alphabet. And it may happen in the question, if they are given capital letter, we are helpless. We are going to use capital letters only if it is given in the question. Okay. Now here number of rows and columns should be same. So say m cross n. So to be square matrix, number of rows and columns should be same. So for example, let us suppose one matrix D is there. 1, -3, 2, then 5, 0, 7, 1, -2, and let us suppose tan x. Now see the order of this. How many rows do we have? Always don't forget, the horizontal line we call rows and vertical line we call columns. Yes or no? Okay, so here how many rows are there? 1, 2, 3. So 3 rows. How many columns? 1, 2, 3. So 3 columns. So since number of rows and columns are same, we call it as the square matrix. Okay. And in this some of the specific term to be taken, just see these elements. See the location of this element. 1 is present in first row and first column. That location is A11. This element 0 is present in second row and second column. So the location of this is A22. And this element tan x is there in third row and third column, A33. So these elements are called diagonal elements. What they are called? diagonal. The elements present in the location of A11, A22, A33 are called diagonal elements. Are called diagonal elements or leading or principal diagonal elements. That's also there. Principal diagonal elements. Okay. Now, let us move on to next. Principal PLE, I think. Yeah. Now, let us move on to the next. In general, if I talk about this matrix, okay. So in general, when we are going to talk about diagonal elements, the diagonal elements will be A11, A22, A33, A44, and moves on up to ANN. And whenever it's a square matrix of order n, we won't specify it's a square matrix of order 2 cross 2 or 3 cross 3 or n cross n. We just say it is a square matrix of order n if it is n cross n. Okay. So now here D is a square matrix of order 3. That's enough. Since I have used the word square matrix, we know from the definition that number of rows and columns should be same. Next comes are called principal diagonal elements or diagonal elements. Okay, this two. Now moving on to next. Diagonal matrix. What is diagonal matrix? It is a square matrix in which non-diagonal elements are zeros. Non-diagonal elements are zeros. For example, see carefully here. 1, 2. And here you see diagonal elements are 1 and 2. Non-diagonal elements are this, both should be 0. I can have one more example. 1, 0, 3. See this example very carefully. There are many wrong myths by the students that as soon as we said diagonal matrix, we just said non-diagonal element should be 0. Who are the non-diagonal elements? Elements other than this. Are they 0? Yeah. Here also elements other than this 1 and 2. Yeah, these are 0. Yes, 0. We never commented about diagonal element. They may or may not be 0. So here I have taken both the elements to be non-zero. Here I have taken one element to be 0. Both are example of diagonal matrix. So in general, we can comment a diagonal matrix A is equal to small aij to be a diagonal matrix whose order is n by n, provided if aij is 0 whenever I is not equal to j. Just see the location. This was the location of this. It is in first row, second column, A21. I mean to say, apart from diagonal elements where the locations of A11, A22, A33, remaining should be 0. Nothing but whenever the index are different. You see, here index are same. For index of same, we are not commenting. Whenever the index are different, here you see A21, this will be, I mean this is A12, sorry, first row, second column. This will be first row, third column. This will be second row, first column. Correct? No. So you can see here very clearly that number of rows and columns are different. Means the location I and j index are different. Whenever it is different, it should be 0. That's what we are commenting. We should know this. Who knows? In MCQ, they may ask this type of question also. Okay. Next, moving on to sixth, scalar matrix. Oops. Scalar matrix. What is a scalar matrix? Again, it's a diagonal matrix. As soon as I said diagonal matrix, non-diagonal element should be zeros and diagonal element should be always equal. For example, you see this 5 here, then here also 5. Order 2. If I take one more, h is equal to, if I take it -7, again -7, again -7, and this is 0, 0, 0, 0, 0, and 0. Okay, this is the example for scalar matrix. So if I try to write a general way of writing, A is equal to Aij of order n is said to be scalar matrix provided Aij obeys the condition that whenever we are talking about diagonal element, for diagonal element the index should be same. It should be equal to a scalar k. So k can be any real number. it can be 0 also. Okay, whereas when it is a non-diagonal element, it should be always 0. Okay, next comes identity matrix. What is identity? Other name for identity matrix is unit matrix. What is identity matrix or unit matrix? It is a square matrix denoted by I, and one suffix is given here will represent the order of the identity matrix, in which non-diagonal elements are zeros and diagonal elements are always equal to 1. So here identity matrix of order 1 will be only this. Identity matrix of order 2, 1 0 0 1. Identity matrix of order 3, 1 0 0 0 1 0 0 0 1. Okay, so this order is 2. That's why I have 2 here. 2 cross 2 it is. This is 3 cross 3, so 3 is given here. This is of order 1 cross 1, nothing but 1 is given here. This we call identity or unit matrix. Now here to write the elements, since and identity matrix is always denoted by I, so I will just write the elements Aij is equal to, always whenever we talk about the diagonal element, it is always equal to 1. Okay, and if I talk about non-diagonal element, it's always equal to 0. Now from here we can generalize or comment. Oh, for a while I think I have touched. Okay, now see carefully, we can just comment about 5, 6 and 7. Every scalar matrix and identity matrix is a diagonal matrix. Okay, so point number 1 we can take as a note. Note number 1, every scalar and identity matrices are diagonal matrix. This type of note you have to make a note. Okay, fine. Whereas every identity matrix is a scalar matrix. Every identity matrix is a scalar. Just make a note here. Kindly make a note of this. So coming to note number 2, what we commented that is every identity matrix is a scalar matrix. So I'll just mention like this: identity matrix implies scalar matrix. The reverse need not be possible, mean to say, point number 3, it need not happen that every diagonal matrix, matrix, as soon as I say this need not imply it is a scalar matrix, and it did not imply it's an identity matrix. So you have to check. Directly as soon as they give diagonal matrix, you will not comment this as scalar or identity matrix. It depends on the context. Usually it will not be a diagonal or identity. That's what I said, did not imply. Similarly, every scalar matrix need not imply that it is an identity matrix. As we are aware, for identity matrix, diagonal elements should be always equal to 1. Scalar matrix need not be equal to 1, but it should be same. So this is about types of matrices. Now let us move on to equality of two matrices. Let I erase it. First, make a note of this. Now let us proceed on equality of matrices. Equality of two matrices. See, as I talk about equality, minimum I should have 2. Even if I just say equality of matrices is also sufficient, but anyway, I'm being a bit specific. So, two matrices A is equal to small aij of order m cross n, and a matrix B, bij of order p cross q are said to be equal if Okay, if this is the matrix, these two matrices are said to be equal, provided, or if, when do we say they are equal? Number of rows, see, they should be of same order. We say two matrices are said to be equal if they are same order. As soon we say of the same order, many will think it's a square matrix. No, 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 need not be. Here we are saying, when I say same order, here M stand for number of rows, that should be equal to number of rows here. Nothing but M should be equal to P. And here N is the number of columns, and here it is Q is number of columns. So N is equal to Q. So this will be the condition for two matrices to be equal, that row should be equal to row and column should be equal to column. For example, if I say one example here, matrix A is equal to 1, 2, 3, 4, 5, minus 7. Again, matrix B should be of also same order, 1, 2, 3, 4, 5, minus 7. Now you see the order of this is 2 rows and 3 columns. Here also 2 rows and 3 columns. This is called equal matrices. And not only that, and their corresponding element should be same. This is the first condition. Second condition is, and their corresponding elements are equal. Corresponding elements are what? Equal. Only then we say it is equal matrix. For example, here we see A is equal to B. But let us suppose I will take the same problem. A is equal to 1, 2, 3. Here 4 is there, 5 is there, and minus 7. And B is equal to, I will take same 1, 2, 3. I'll use some different letters here. C here, and here it is D. And here 4, 5, and plus 7. Favorite mistake by the student, no? As soon as they see, they will not see that minus 7 is not equal to plus 7. They are not equal. Since they are not equal, other elements are same. 1 is equal to 1, 2 is equal to 2, 3 equal to 3, 4 equal to 4, 5 equal to 5. 7 is not equal to minus 7. Therefore, matrix C is not equal to matrix D. Similarly, you can see here, in matrix A and B, 1 equal to 1, 2 equal to 2, 3 equal to 3, 4 equal to 4, 5 equal to 5, and minus 1 equal to minus 7. Corresponding element should be same. Okay, not in the order. So both the conditions should be true. Here the order is 2 cross 3, as we already have it. Okay. Now, having understood this, let us try to proceed with the operation on matrices. Now, coming to operation on matrices. Operation on matrices. What are the different operations we can think of to be performed? First operation will be addition. For a while. Yeah. Two matrices. Condition for two matrices for addition is order should be the same. Nothing but number of rows of both the matrix should be equal and number of column of both the matrix should be equal. Okay. So let us suppose that I have got a matrix A, 1, 2, 3, minus 4, and 1 here, 7 here. And I have got a matrix B here, 3, 1, 2, and 1, minus 7, 5. See the order of this, 2 rows and 3 columns, so 2 by 3. And here 2 rows and 3 columns, so 2 by 3. Okay, 2 cross 3 or 2 by 3, that's how we pronounce. So addition A plus B. How are we going to add? Corresponding element should be added. Meaning to say, this is the first element, add with this 1 plus 3, 4. And here 2 plus 1 will be 3. 3, 1 plus 2 will be 3. 3 plus 1 will be 4. Minus 4, minus 7 will be minus 11. 7 plus 5 will be 12. And what's the order here? 2 rows and 3 columns. So here, whenever you perform any matrix operation after addition, the order will be the same as the given matrix. So who knows, for 1 marker, means in our CET, as soon they have given what? Addition of two matrices, they have added and given you a matrix. And if they ask you what could be the possible order of the given matrix, you can just see whatever the order they have given, same order both will be. Both will be. Okay. That will be 2 cross 3. Fine. Similarly, one example we take on how are we going to take for square matrix also. A is equal to, suppose 2, minus 1, 3, and 0, and B is equal to, let us suppose 1, 2, 5, and 7. And again, we want to add these two matrices. And here the order you can see 2 rows and 2 columns, so 2 by 2. Here also 2 rows and 2 columns, nothing but 2 by 2. Correct now? So come on, add 2 plus 1, 3. Minus 1 plus 2 is 1. 3 plus 5 is 8. 0 plus 7 is 7. And order is what? 2 by 2. So as soon I came to know what will be the what is the addition order, we can also comment about what is the given matrix order as well. They'll always remain same. Okay. And one more thing you can see, rectangular matrix will remain rectangular, square will remain square after addition as well, as order remains same. Now, let us also understand multiplication of a matrix by a scalar. Multiplication of a matrix by a scalar. We are multiplying a matrix by what? A number, by a scalar. So let us suppose that we have got okay, here also just comment in general that if at all we have got a matrix A, small a ij of order m cross n, and B is a matrix Bij of order p cross q. For addition, so A, okay, capital B here, A plus B is equal to some matrix Cij can happen provided what? Provided number of rows equal to number of columns, and number of rows equal to number of rows of the both the matrix, and number of columns should also be same. Only then addition is possible, and the order of this will be same as given matrix, either m cross n or p cross q. Fine. So having understood this, let us have here one word then. Is it simple? Okay, fine. Coming to scalar multiplication, let us suppose that I have got a matrix A. One example we take here, and it is some 2, 3, 7, then 5, 2, and 9. If this is given to us, they are asking us to find what will be, suppose 2A. So I am going to multiply a scalar 2. Scalar means any real number, it can be 0 also. Multiplying to 2 was the answer. So you have to multiply this 2 to each and every element. So 2 into 2, 4. 2 into 3, 6. 2 into 7, 14. 2 into 5, 10. 2 into 2, 4. 2 into 9, 18. What's the order of this? 2 cross 3. Here also the order 2 cross 3. So even scalar multiplication also will not change the order of the matrix. So in general, if I want to define, if we have a matrix here, Aij, need not be a square matrix. You can see here I have taken a scalar means a rectangular matrix of order m by n. Then k into A will be k multiply. Then I can multiply this k to each and every element, and then also the order will remain same. Okay. First, kindly make a note. Okay, so let us having taken one example here, let us also try to take an example for square matrix. So if I take a matrix of order 2 by 2, I suppose 2, minus 1, 0, 3, and then I want to find suppose 7 times of A. So I have to multiply 7 to each of the terms. So 7 times of matrix A is 2 minus 1, 0, 3. Multiply them. 7 2s are 14. 7 into minus 1, minus 7. 7 zeros are 0. 7 3s are 21. Here the order is 2 by 2. And here is also what? 2 by 2. As you can see, 2 rows and 2 columns. Order will remain same. That's what we commented here. As I said previously also, if I write 2 different letters, it may be square matrix or it may be rectangular. This always chance that I can say n is equal to m. But if I write here n by n or m by m, no, there is no chance about rectangular matrix. Okay. Now I'm just getting a doubt now whether you are able to see this one or not. So I'll do one thing. I'll just rewrite that one here properly so that no things should be clear. So what I'm saying for addition, what I'm saying is for addition, I'm saying that if we have got a 2 matrix, A is equal to Aij of order m by n, and B is a matrix Bij of order P cross Q. Okay, then for addition to be defined, A plus B, and I'm getting that to be some matrix Cij after I add this matrix. Okay, first right step by step. So Aij m by n plus bij p cross q. P cross q. So if I add this and if I get a matrix Cij, if at all I want to get this, first row should be equal to row, nothing but m should be equal to p and column n should be equal to q. Only then we can have addition, and the order of this will be surely m cross n or p cross q because both are same. I hope this is clear. This will be the condition for addition of two matrices. Okay, now having understood all this, let us try to have properties. As I said, and before I go ahead, one matrix I would like to discuss: negative of a given matrix. A matrix is given to you, and we are supposed to find negative of a given matrix. So any matrix A, if it is given as A I J, the negative matrix, if A is given this, then negative matrix is negative matrix is minus A, and again if the order is m by n, it will remain again m by n only. Okay, so for one example, can be if A is given as 1 2 3 minus 1 7 5, then minus A, I've just multiplied negative in, so what I'll have, minus to plus is minus 1, minus to plus is minus 2, minus to plus is minus 3, minus to minus is plus 1, minus to plus is minus 7, minus to plus is minus 5. This order is 2 by 3, and again it is 2 by 3. And the same thing can be quoted for square matrix as well. So I hope these things are clear. So who knows, for one, in CET they are giving one question, and what about negative concepts are really important. And as I said, in case of you people going through all the videos of PUC, I think 3 to 4 videos are there. I thought I will give all the synopsis together, okay, in quick manner. Kindly make a note. Now let us move on to multiplication of two matrices. Then I will quote all the properties. Okay, coming to multiplication or product of two matrices. Let's suppose that we have got a matrix Aij, whose order is m by n, nothing but number of rows are m and number of columns are n, and B is a matrix Bij, whose order is p cross q, number of rows is p and column is q. Then when I want to multiply the two matrices A into B, so let's substitute here. A is this, m by n is the order, and Bij, the order is p cross q. Matrix multiplication exists provided number of column of the first matrix, that is n, is equal to number of row of the second matrix. So this multiplication exists if n is equal to p, number of rows should be equal to number of column, and after we multiply we get one matrix, let's say Cij, and this order will be equal to number of rows of the first matrix and number of column of the second matrix, that is m cross q. This will be the matrix order. Now let us take one example. I'll take both square and rectangle matrix. So one example here. Example: if matrix A is equal to 1 2 3, let's take first a square matrix, and B is equal to minus 1 2 7 and 3. Okay, so 0. Let us have all the numbers. Now this is 0 minded. Now the order of this matrix is 2 by 2. This is also 2 by 2. Now I can think of performing multiplication. Now I want to perform multiplication. Just see carefully. This first row should multiply to first column. Always while performing multiplication, remember, as you know, this stands for rows and this stands for column. Think perpendicular. Okay. Row should multiply to column. As soon as you multiply to column, just see carefully. Corresponding elements should multiply. 1 into minus 1. Let us go in detail. 1 into minus 1. Then 2 into 7. You can see now, plus here. 2 into 7. you can see we are multiplying corresponding elements. We are multiplying corresponding element 1 into -1 and 2 into 7. Now, as soon as we finished the entire column element, we have to go for a new column. Okay, when I go for a new column, I have to give a space. Whenever you go for a new column, you have to give a space. Now here, 1 into 2 plus 2 into 0. As for the second column, there are no more columns, close the bracket. And to avoid confusion, also very simple. You see this location. This location is there in first row, second column. What? This location, this entire element 1 into 2 and 2 into 0 is there in first row, second element. So we are multiplying the first row and second column. I repeat again. This is present in first row, second column. So it means when I'm multiplying, you are multiplying first row with the second column to get the answer. Similarly, you see this particular location is what? Second row, first column. That's what you can see here. Second row, first column you are multiplying. So 3 into -1, then plus 4 into 7. Similarly, second row, second column, 3 into 2 plus 4 into 0. So now 1 into -1 is -1. This is -1. Then plus 2 into 7 will be 14. 1 into 2 is 2. 2 into 0 is 0. 3 into -1 is -3. 7 fours are 28. 3 into 2 6 plus 4 into 0 0. You have to give a space. Be careful. Now what is the here we have went for A into B, correct? No. So what's the final answer? Therefore A into B will be -1 plus 14 will be what? 13. This will be 2. This will be 25. And this is 6. What's the order again? 2 rows and 2 columns. Whatever I have said about the obtained matrix order need not be so much clear if it's a square matrix. So for square matrix, there is no problem. Just we'll get the same. Whatever one matrix order is the same thing, you can write it. Okay, without checking anything or without knowing anything. Without much thinking, you can comment. But now you see this. If I take a matrix C, 1, 2, 3, 4, and matrix D is 2 rows, okay, 2 and 4. Now see the order of this. Purposely I'm taking one square matrix, other is a rectangle matrix. Here the order is 2 by 2, and here the order is 2 cross 1. So number of column and rows are same. Number of column of the first matrix and number of row of the second matrix are same. So matrix multiplication exists. Now let us perform multiplication. C into D. What is C? 1, 2, 3, 4. What is D? 2 and 4 here. Now let us perform multiplication. So for here, row versus column, we have to go ahead. So row and column. This is the row, right? So if I perform row versus column, see carefully. 1 into 2, 2. Then 2 into 4. So plus 2 into 4 is 8. I'm just taking together and simplifying. I don't have one more column, so I have to close it. See the way I gave a gap here because I had a one more column. Space I gave there, correct? But here is no one more column, so stop there itself. Next, no space is given here. Okay, next. As soon as I go for second row here, yeah, I'll go second row here. Second row here, 3 into 2, 6. Plus 4 fours are 16. Now add this. 2 plus 8 is 10. 6 plus 16 will be 22. What is the order of this? Check it out. 2 rows and only one column. 2 by 1. Now if you just see for matrix here, see this? 2 cross 1. That's what we got here. Okay. So I hope this point is clear. Now one question might come, sir, what if it violates the condition? Fine, let us take one example for that also. What if it is violating that number of column of the first matrix should be equal to number of row of the second matrix? If it is violating, what is going to happen? Why matrix multiplication not possible? Let's take one example. Let us take the matrix E here. So I'll take here 1, 2, 7, minus 1, and matrix F. Let us suppose here 2 rows, 2 column. No, so I'll just take 1 and 3. So here the order is 2 rows, 2 column, and here it is 1 row, 2 column. Now you can see 1 row, 2 column. So you can see here that it's violating the condition that number of column of the first matrix and number of row of the second matrix are not the same. Now if I multiply this E into F, see what's going to happen. 1, 2, 7, minus 1. Then here 1, 3. Correct? Now see carefully. When you want to multiply this 2, see, first row, first column. 1 into 1, fine, you will get 1. But this 1 into 1 is 1, you got. But this 2, you don't have any element here to multiply. You don't have any element to multiply here. That's the reason we are saying this condition, that number of column of the first matrix should be equal to number of row of the second matrix. Some might say, sir, I can add 0. No, 0 don't have any value, so I can add 1 0 here. No, be careful. Write it here. For this matrix 1 3, as soon you write 1 0 here, you have changed the order. 0 don't have value, yes, but what is matrix? Arrangement of numbers, elements of functions, correct? No, in rectangular array. So you are arranging the objects. 0 is one of the objects. So adding 0, as soon you do, it is no more 1 plus 2, it will become 2 plus 2. And as soon as 2 plus 2, the number of column of the first matrix and number of row of the second matrix will be same, nothing but going with this condition only. I hope this point is clear. So I hope also you have understood and recall the how we are going to multiply two matrices. Kindly make a note. Okay. Dear students, now let us move on to properties. So now, first coming to the properties under addition of two matrices. Addition of matrices. See, coming to the addition, first one is commutative. See, I don't want that again commutative property. I give the heading properties, so we're talking about properties only. So if I talk about two matrices, now here when I'm talking about two matrices, it means addition should be performed, but order should be the same. That is obviously, that is defined. Number of rows of both the matrices are equal, number of columns of both the matrices are equal. Only then we are talking about the properties. If addition is not possible, there is nothing to talk about properties. Okay. So commutative, if I have got two matrices, A plus B same as B plus C. Second, associative property. Associative property. If I have got three matrices, A plus B plus C, either I can add first A plus B, or I can add B plus C, then add with A. Similarly, after adding A plus B, you can add with C. Next, additive identity. Additive identity. This is, see, here also, no, when we talk about two numbers, 2 plus 3, it is what, 5. But at a time, even though we have got addition of basic two numbers to add, but at a time we can have only two numbers. If I have given you 2 plus 3 plus 7, now at a time we cannot add all the three. Either you are going to add 2 plus 3 first and then add with 7, or you are going to first add 3 plus 7 and then add with 2. That's what both of you are equal. That's what we are seeing here also, associative. At a time we can add only 2, so the order is not important. Next, additive identity. Recall in your school days under real numbers, which is that number if I add with 7, I'll get back 7. It is 0. Same as 0 plus 7. So for any matrix I said. So here, whichever matrix I'm talking about, as I mentioned here, A is equal to Aij of order m cross n, and B is equal to Bij of order m cross n. Nothing but the given matrix need not be a square matrix. But it is true for, this is true for rectangular matrix as well as square matrix. Okay, provided the addition condition is defined. Now for additive identity, for every matrix A, 0 matrix. Okay, if I add, I'll get back 0 plus A, nothing but A itself. And 0 matrix can be of any order, but it is same as matrix A order. I mean to say, if this is m cross n, it should be also m cross n. Only then addition is defined. So additive identity is 0 matrix. Next, after additive identity, additive inverse. Additive inverse means if I've got a number 7, which number should I add here to get back additive identity 0? That is minus 7. Similarly, minus 7 plus 7 will be again 0. So for any matrix A, if I have negative matrix A, only then I get additive identity 0 matrix. The same as minus A plus A. So additive inverse is minus A, negative matrix. Okay, don't forget what is minus A, negative matrix. Already we have discussed negative matrix. This is all the properties of addition. Now let us move on to scalar multiplication. So properties of scalar multiplication of a matrix. Scalar multiplication of a matrix. So I've been given a matrix. I want to multiply by scalar. So let us suppose again the matrix A is supported m by n. So the first thing is, if I've got K and is multiplied to a matrix A plus B. So either I can first add the matrix A plus B and then multiply by scalar K, or I can first multiply the scalar K to A and scalar K to B, and then I can add. That's the point. Next, similarly, K plus CL, I've got two scalars. K is any scalar, any real number. I've got two scalars and I want to perform with the matrix A multiplication. Either you can add both the scalars and then multiply with matrix A, or you can multiply the scalar with matrix A, K into A, then L into A, and then you can add them, you'll get the same. Okay, this is about scalar multiplication of a matrix. Now let us move on to properties on addition over. Okay, now properties on multiplication of matrices. Multiplication of a matrix. Before I go ahead, now I think I have just forgotten about in types of matrix, zero matrix. I just say here in types of matrix. Now I have forgotten about zero matrix. Sorry for that. So what is zero matrix? Zero or null matrix. I think I forgot to discuss that. Now I realized. Zero matrix denoted by capital letter O. Okay, and all the elements should be zero. Only then we say it is zero matrix. It is say 2 by 2. And again, if I say O, it can be 0, 0, 0, 0, 0, 0. It can be a square matrix and can be also a rectangular matrix, where each and every element should be 0 and given by capital letter O. Okay, fine. This is under types of matrices. Types of matrices. Okay, types of matrices. I just forgot to mention, I think, this types of matrices. Okay, now let us move on to the multiplication of matrix properties. First thing, now again, matrix multiplication be defined. A into B need not be equal to B into A in general. So we have to always check. We have to always what? Check this. Directly will not comment it's not equal. You have to check. It may be, I may not be. After I just finish this now, I'll discuss even the particular case when it is commutative. Okay. So commutative need not be commutative. Need not be commutative. Next, associative. Associative. Yeah, it is always associative. If I have got three matrices, I think here I have not given matrix C. Okay, matrix C will be Cij. And here for addition it is M cross N. And here, as you know, here matrix multiplication should be defined. Okay, so only then we are going to talk about. So A into B into C. Either I can multiply AB and then multiply with C, or A multiply with B and C. Okay. Next comes multiplicative identity. So it is point C. Multiplicative identity. Same as a real number. Recall, if you have 7, which number should I multiply here to get back 7? It's 1. Similarly, 1 into 7 is 7. So 1 is the multiplicative identity. Similarly, for any square matrix. Now here it should be a square matrix. So here is a square matrix. So A into I will be equal to A is equal to I into A. Now A is a square matrix. Only then this property going to hold good. So only for square matrix this law is going to hold good. Remaining all can be rectangular matrix as well. For this also it can be a rectangular matrix. It don't be a square matrix. But for multiplicative identity, it should be only a square matrix. and I is the identity matrix, as we know, where I is identity matrix. Okay, now having understood this, let us move on to the last one, that is distributive property. See here, here A into B plus C is same as AB plus AC. Mean to say, you can multiply AB, then you can multiply with AC. Either you can add BC and then multiply with the A, or perform multiplication with AB and then AC, then add. Again, order, the condition for multiplication, order the order is that it should be defined. Similarly, it can also happen that I have got A plus B, then I have got into C, then also A into C plus B into C. Okay, fine. This is what we have got. So now let us try to discuss under what condition it can be commutative. Okay, kindly make note of this. Okay, before I forget, this law, what we call this law, this both, it is known as distributive law. Distributive law. Okay, or distributive property. Now let us move on and let us try to understand what will be the basic condition for commutative. And here, if you see, multiplicative identity, A into I and I into A. Now here it is commutative, right? So under some special condition or cases, matrix multiplication is commutative, but need not be always commutative. Okay, so it's non-commutative in general. Now, if I just consider a matrix A, okay, of order m by n, and matrix B, Bij, of order p cross q. If this is given to us, then under what condition A into B is equal to B into A? Let us try to understand. If I talk about A into B, after I multiply, I get one matrix Cij. And if I go for B into A, after I multiply, and suppose I get a matrix Dij. Now first recall the order for A into B. Here number of, since A is first, B is second, this is called pre-multiply. A is before B, no, so A is called pre-multiple of B, or B is called as post-multiple of A. B is called as post-multiple. What is pre-multiple, post-multiple? Whenever any matrix is there before the matrix under multiplication, so then this matrix is called pre-multiplier. Pre-multiplier. Now since matrix B is present after A, then this matrix B is called post-multiplier. Same like mobile charge, no? Postpaid, prepaid. Postpaid is what? First utilize the services and then pay the amount. Prepaid, first pay the amount and then utilize the services. Same thing. Okay, before, whenever a matrix is multiplied before, that is called pre-multiplier. After, it is called post-multiplier. Okay. Now, if you just see here, for matrix multiplication to be existing here, we know that for here, okay, n should be equal to p. So for this to be defined, n should be equal to number of column of the first matrix and number of row of the second matrix should be same. N is equal to p. And the obtained order m cross q I will get. Am I right? Number of rows and number of column will get. Whereas for B into A to be defined, I'll write again here, B. I'll write again here, bit separately, B here, then A here. What is B order? P cross Q. And what is A here? M cross N. This is giving us the matrix Dij. Now for this multiplication to be defined, first, since here B is the first matrix and A is second matrix, number of column of the first matrix B should be equal to number of row of the second matrix A. Nothing but Q should be equal to M. And after you multiply, these two should be same. P means, I mean to say, the order should be P cross N, not same P cross N. Okay, this should be the order. Now what we want to understand is under what condition if AB should be equal to what? BA. Nothing but if it is commutative, what should be the basic criteria, necessary condition? So for AB, this matrix we got. And for BA, we have got the matrix DIG. And the order of DIG is P cross M. So when do we say matrices are equal? For two matrices to be equal, order should be same. So M should be equal to P. And Q should be equal to N. We have got one condition here. And we also got here condition N is equal to, and here also no, yeah, N is equal to P. And Q should be equal to M. Come on, combine all this condition. This condition is for what? Multiplication to be defined A into B and B into A. And for equality, this condition. Now just see carefully in terms of order I'm talking about, not in terms of corresponding element presently. So here M. So if I combine this condition 1 and 2. So if I combine 1 and 2, combine 1 and 2. Combine 1 and 2. M should be equal to P. But M is also equal to Q. And P is also equal to N. Oh, what's the meaning of this? All the number of rows and columns should be same. Nothing but M and N and P and Q should be same. Nothing but if at all commutative holds, it's only for square matrix. It can't be for rectangular matrix in terms of order. Then surely corresponding element should be also same. So as soon as that corresponding elements are same, only then it is commutative. But for commutative, it should be a which matrix? It should be a square matrix. Let us comment that. This is taken. What I comment here? Also comment the necessary condition. Here it is N. So from here we can comment the necessary condition. The necessary condition for two matrices to be commutative, the given matrices should be a square matrix. Square matrices. It's a basic. Doesn't mean that as soon as you have got the square matrix commutative. I'm just trying to say that as soon as you see that it's a rectangular matrices, without checking you can comment. See, questions like this. There are two matrices given to you. And you have to comment whether it's commutative or not. You have to check, no? So what I'm saying is as soon as the two matrices are given and and as soon you came to know that the order is not a square matrix, means it's not a square matrix, number of rows and columns are not same, then you can directly comment it is not commutative, no need to multiply and check. Whereas if it is square matrix, then you have to multiply and check. Okay, kindly make a note. Now let us move on to the next point. See, whenever we talk about any two numbers, take as a note. See, we know that coming to real number A and B, not matrix, real number. If A into B is 0, product of two numbers is 0, then this implies either A is 0 or B is 0. Oh, wait, before I go for this, no, coming to commutative only. So this matrix, if I take two square matrix, just see A into B and B into A of this. If you multiply A into B, row, column, correct, no? So since I have already taught you the matrix multiplication, let's see A into C is AC, 0 into 0 is 0. Then second column, A into 0 is 0, 0 into D is 0. Next, closing the bracket because column got over. Now coming to second row, 0 into C is 0, B into 0 is 0. Next, second column, 0 into 0 is 0, B into D is BD, so P into D. So A into B, we have got AC 0, 0, BD. This is equation number 1. Now let us talk about B into A. What is B? Here C 0 0 D, and A is this A 0 0 B. Now multiply this row versus column. This is first row, second column. C into A, 0 into 0 is 0. Then C, second column now, C into 0 is 0, A 0 into B is 0. Again, second row, first column, 0 into A is 0, then D into 0 is 0. Then second row, second column, 0 into 0 is 0, D into B is DB. Now what we are going to have? C into A is same as AC. Under real number, it's commutative, real number. A, B, C means the elements all are real numbers. 0 plus 0 is 0, then this is also 0, this is BD. See this and see this. Both AB and here this BA, no? Both these are equal. Oh, what's the meaning of this? What is this? Which type of matrix is this? First, let's comment here. AB is equal to BA from equation number 1 and 2. Which type of matrix is this? These are diagonal matrix. So whenever you have got diagonal matrix, it's always commutative provided multiplication is defined. So is it multiplication defined? My square matrix, obviously multiplication defined, no, need not be. If I have taken this as 2 cross 2 and if I have taken this as 3 cross 3, now it's not defined, no? Fine. So for diagonal matrix, that implies product of two diagonal matrices commutative. Product of two diagonal matrices is always commutative. Okay, fine. Now coming back to this, what we are saying is, if your product of two numbers are 0, any one should be 0. Is it the same thing in matrices? Check it out. If I take two matrices, here, I suppose here 0, then 1 here, 0, then 2 here, and 1, some 7, 0, 0. Now let us multiply this. What if we multiply this row versus column, correct? 0 into 1, 0, 1 into 0, 0, 0 plus 0 is 0. 0 into 7, 0, 1 into 0 is 0, 0 plus 0 is 0. 0 into 1, 0, 2 into 0 is also 0. 0 into 7 is 0, 2 into 0 is also 0. Oh, but none of this is also not a 0, null matrix, this is also not a null matrix. When do we say the given matrices are equal? When do we say the given matrix is 0 matrix? All the elements should be 0, like this. So what we can say is product of two number is 0. It means any one should be 0. In matrices, it need not be. Product of two matrices, if I get 0, doesn't mean that one of the matrices is 0. It can happen that both the matrices are non-zero. Okay. So product of two matrices 0 doesn't imply that any one of the matrices are 0. Even both can be non-zero also, as you can see here. Okay. Fine. So I hope this point is clear. Now let us move on to the next part. First, you make a note of this. We'll take the last. Dear students, we have understood that if two matrices are non-zero, then their product can also be 0, maybe 0. But you should also understand that, as you know, in I can take as note number 2, whatever we discussed for previously, that product of two matrices, if it can be, I repeat, product of two matrices can be 0, even though both the matrices need not be 0. Now here what I want to stress is, same like our real number, if I have got A into 0, surely I should get back 0 only. Similarly, under matrices, let us suppose any matrix A is multiplied by a 0 matrix, the answer will surely what? 0. And it is commutative nature, nothing but A into 0 matrix or 0 into A matrix, it will be again what? 0. For example, because I don't want you to forget this point. For example, if I got a matrix A, let's suppose 1, minus 2, 3, 1, and now I'm taking a product with 0. So now here 1, minus 2, 3, 1, then 0, 0, 0, 0. I just want to highlight, and I want you to remember that surely if any one of the matrix under multiplication, if any one of the matrix is 0, product is definitely 0. No doubt about it. And you can see here. Multiply row versus column. 1 into 0, 0. Minus 2 into 0, 0. 0 plus 0, 0. Now moving to second column. 1 into 0, 0. Minus 2 into 0, 0. 0 plus 0, 0. 3 into 0, 0. 1 into 0, 0. 0 plus 0, 0. 3 into 0, 0. 1 into 0, 0. Okay. So we got a null matrix. This point I wanted to highlight that always whenever you multiply any non-zero matrix with a zero matrix, the output is always a 0, and it need not be a square matrix. I can also have one more example you can take here. I can also have a rectangle matrix. For example, I take B is equal to 1, 2. Yeah. Now I take 0 matrix such a way that multiplication is defined. Here the order is what? 2 rows and 1 column. 2 cross 1. So surely I'll just take a null matrix. Now see this 1 here, 2. So it is 2 cross 1. So I can just take the order such a way that 2 cross 1. So I can have only, yeah, enough. Just have to match with what number of column of this matrix. So since the column is 1, I can have only 1 column. Row I mean to say, since number of column is 1 in the matrix B, I can have number of rows will be 1, so that multiplication exists. Column can be any number. I can have only 1 column or more than 1 column. Doesn't matter. Now how are we going to multiply? 1 into 0 is 0. There are no more column, so I have to go for the new row, second row. So close the bracket. 2 into 0 is what? 0. So again, it is a 0 matrix. See, the output is 0 here. This 0 need not be the same 0 matrix. You can see here. Here it is now 2 cross 1. And that is expected, no? Whenever you multiply two matrices, the obtained matrices order will be number of row of the first matrix and number of column of the second matrix. Okay? Fine. Kindly make a note of this. Okay. Dear students, now let us move on to transpose of a matrix. If the matrix is given to you, say a general matrix, if I take A is a small aij, where number of rows are m and number of columns are n, then the transpose of the matrix A is denoted by either A dash or A T. Our will be T, the first letter of the word transpose. Here we are going to interchange row to column and column to row. Even the index I, I stand for row and J stands for column, so they will get exchanged. So I'll get A, J, I and N cross M. This will be the transpose of the given matrix. For example, if I say that we have got a matrix 1, 2, minus 7, let's add some more element here, 4, 1 and 3. Let us extend this. And the order of this you can see. How many rows? 1, 2. There are 2 rows. And how many columns? 1, 2, 3. 3 columns. Then the transpose of this, any one of the symbol can be used. Okay, A power T or A prime. So the transpose of this will be, this is the first row. Change to column. 1, 2 minus 7 will change to first column. It was first row here. Now it's the second row. 4, 1, 3 will change to second column. I repeat, the second row will change to second column. And now what's the order? How many rows we have? 1, 2, 3. So there are 3 rows. How many columns? 1 and 2. So you see, whatever the order we had here, it is getting exchanged. That's what I commented here. See, you should also understand, who knows, no, for 1 marker, means for MCQ. See, they can also ask, which is a matrix? Even if you take the transpose, order will remain same. Which is a matrix? Even if I take transpose, the order will remain same. The order can remain same provided it's a which matrix? Square matrix. For example, a 1, 2, minus 1, 4. Order is 2 by 2. Even if you take transpose also, this row will become the column. This second row will become second column. And again, the order is 2 by 2. So only for square matrix, order will remain same even if you take transpose. Okay, fine. Now, as we said here that the location will change. Just here the location is, the index will change, I mean to say, A11, and here it is what? First row, second column, no? A12. What is this? First row, third column, so A13. As soon as you transpose, yeah, see, there is an element. Okay, here I'm going to say element with the index I and j same. There won't be any change in that, correct? So here also this is the second row, second column, so A to 2. That is not going to change here also, A to 2. So element with the same index. I'm not using the word diagonal elements here because A is not a square matrix, B is a square matrix, so I can use the diagonal elements word for this matrix. Now here you see this 2 which is present here. Now the location of this 2 is second row and first column, so A to 1. So whatever the location was there, it has got exchanged. So 1 2 became 2 1. Similarly, you see minus 7. Minus 7 is there here. This is the third row and first column. So A 3 1. Okay, I hope this point is clear. So having understood this, let us try to move to a very important type, that is symmetric matrix. A matrix A, square matrix A, most important, it should be a square matrix A, is said to be symmetric if A transpose is equal to A. On taking transpose, I should get back what? The same matrix A. For example, if I talk about A is equal to 1 2 3, okay, here I'll take as 2. Then what is the transpose of this? If I take the transpose of this, I'm going to have this, the first row will change to first column, second row will change to second column. This is same as this, nothing but A. So A transpose is equal to A, and it should be a square matrix. Now here, understand still better. If I say matrix A is taken as A, I, J, and let us specify here it should be a square matrix, so n by n. So here the element of this matrix is A, I, J. On transpose, as I said, the index will get exchanged. The index will get exchanged. I, J will change to J, I. So here it is A, J, I. So just see this carefully. What's the meaning of this? Apart from the diagonal element, whatever the index is there now, the exchange of index when it occurs, those corresponding elements should be same. See this. Here, when I was writing, I wrote 3 here. Again, suddenly I changed. How? I realized that this is the diagonal element. A11 is this, A22. This element is A12, first or second column, and this is what? Second or first column. These two should be what? Same. Only there it will be A transpose equal to A. Okay. That's what it is given here. Coming to skew symmetric matrix. Skew symmetric. Okay, before writing skew symmetric matrix, let I give one more example here for you of order 3 by 3. So see the way I'm writing matrix B. When I'm writing, I'm very much precaution that first I write diagonal element left to right. But when I'm writing this element, see 4. After 4, I should make sure this should be also 4. Why? This is first row, second element. This is second row, first element. Aij should be equal to Aji. Only then it will be symmetric. But in PUC, we have always taken like this. Take the transpose, then compare the equal. Now we are in CET. We are just going to go for still more detail. It's not a shortcut. We have understood the definition still more better. Hope so recording. Yes. Now see, if I here minus 7, then this corresponding element will be also minus 7. Reason, this location is first row, third column, A1, 3. This is also third row, first column. So just see, index got exchanged, elements are same. Similarly, if we have got something like, let us suppose A here, then this should be also A. Again, this location what? Third row, second column, 3, 2, and this is second row, third column. So A, 2, 3. Okay, I hope this point is clear to each one of you. Okay, fine. So here you can see very clearly, if I take B transpose, even with the definition, this is the first row, will change to first column, 1, 4, minus 7. Second row, 4, 0, A will change here, 4, 0, A here, and third row will be third columns, minus 7, A and 7. And you can see it's the same as this matrix, nothing but B transpose is equal to B. Okay, now coming to skew symmetric matrix, a square matrix. Again, if a given matrix is a square matrix, nothing but Aij, n by n. So skew symmetric matrix and symmetric matrix both are what? Square matrix first. And if I take transpose on this matrix, I should get negative of A. Only then I say it is a skew symmetric. Now again, Aij, is right here, Aij, and here it is Aji. So here it should be same, but here should be negative. See, Aij and Aij and Aji sign will be opposite. To compensate that sign should be same, we multiply with negative sign. Let us make you understand here. See this carefully. Let's do the example here. Example for skew symmetric. If I talk about C is equal to 0, 0 and 2, I write minus 2 here. Now the question is, to check is it skew symmetric or not, first I will apply this condition. See carefully. If I take the transpose, C transpose is equal to, this is the first row, it change to first column, 0, 2. Second row will change to second column. Now are they equal? 0 equal to 0. First order is same, 2 cross 2, 2 cross 2. Now this is, and I hope you understand now why we say for symmetric and skew symmetric it should be square matrix, because if it's a rectangular matrix, as soon you take the transpose, you can see order is different. When order is different, it cannot be equal matrices. First condition for two matrices to be equal is first order should be same. Then I should talk about the corresponding elements are same or not. Okay, now come here. So that's the reason it should be always a square matrix. Now you see 0 and 0, fine. Here it is 2, but here it is minus 2. Here it is minus 2, but here it is plus 2. 0 and 0. So the signs are not matching. So if I take minus common, so 0 problem. Minus into minus plus 2. Minus to plus minus 2. And then 0. This is same as this, nothing but C. So minus C and here C transpose. C transpose is equal to minus C. Therefore C is equal to what? 0, 2, minus 2, 0 is a skew symmetric matrix. Skew symmetric matrix. Now there will be some questions, sir. Is the diagonal element should be 0 always? Why you have taken, or is it taken by chance? Let's have a discussion. First, kindly make a note of this. Dear students, as we are talking about the diagonal elements of a skew symmetric matrix, I have taken 0. Is it by chance or is it mandatory? Let us understand. For that, I am taking this condition again here. That is Aj is equal to minus of Aij. Now, since I am talking about diagonal elements of a skew symmetric matrix. So I take this as equation number 1. Now for diagonal elements, we know that the index should be same. So as you can see here also, this is A11, this is A22. So I and J should be same. So if I put J is equal to I in equation number 1, so this will turn to be A in place of Ji. So here Aii is equal to minus Aii. If I transpose this, Aii minus change to plus Aii is equal to 0. So I can add this 2, I'll get 2 times of Aii, or this will be Aii is equal to 0. So very, very important. This implies the diagonal element should be always 0. This implies diagonal elements of a skew symmetric matrix are always zeros. Always zeros. So it's not by some chance, it is actually. And next, I also want to understand the significance of this minus here. Many will think, no, so here positive number is equal to negative number. No, not at all. Let us take this matrix C again here. Matrix C here, we have 0, 2, minus 2, 0. What is the location of this 2? It is there in first row, second column. Nothing but this index is first row, second column, right? And this location is second row, first column. So A21 is minus 2 and A12 is 2. Okay. Now see, equate them. Is minus 2 is equal to 2? No. That's what you see here. This is actually what? A21. and this is what A12. Since signs are not same, so we cannot say they are equal. That's the reason we are adding one minus sign here. So this minus sign is given so that whatever the negative term is there here, then this is positive. This entire thing you can see now here, this is only positive. So plus into minus minus, this is already negative. So that's the reason minus is given here. Okay. So don't think that no positive is equal to negative. And many students will think this is positive because plus sign is there here. See, plus sign is there, but the element which is there may be negative or positive. I have this point is clear. Similarly, when I'm saying it can also be like this, no, that I could have taken the plus here and minus here, and this is A12. Then again, this negative when it is given, for example, let us suppose here this was a positive quantity, which is already positive quantity. Let us suppose this is negative quantity, then minus multiplied so that the output will be a positive, provided here we have positive. Okay, fine. So even 3 cross 3 also we can have one example. Directly you can see if I take matrix B here, 0, 0, 0, diagonal. Even if one diagonal element is non-zero, then it's not a skew-symmetric matrix. Recording, no? If I have got 3 here, surely here it should be minus 3. So you can see, no, that diagonal element is acting as a mirror. These are the image. So image should have opposite sign in skew-symmetric. If I have got 7, there should be a minus 7. If I have 0, whether here plus 0 or minus 0 doesn't make any difference. Okay, I hope this thing is clear. Now let us try to understand some of the important theorem on this. Kindly make a note. Yeah, here, no, I just wanted to comment here, minus 7, so plus 7, 0 or minus 0 doesn't make any difference. So for this I am not bothered to give any sign for 0. Okay, kindly make a note. Okay, now let us try to understand properties of transpose of a matrix. Now coming to transpose of a matrix. See, the first property, if I take transpose twice or even number of times, I'll get back the matrix here. Second, addition of two matrices if I take, and if I take the transpose, then I can also take the individual transpose. Here you should also understand it can be a minus sign also, no problem. When I'm talking about this, you should also understand that when we went for addition, no, of the matrices. Okay, let us first complete this. So third one is here. So if I talk about scalar is there and a matrix, and I want to take a transpose, scalar will not get affected, only matrix will get transpose, because we are changing row to column and column to row. So scalar is just a number, no problem for that. So k is any real number. Next, if I take a transpose on the product, the order will change, B transpose into A transpose. If I have got similarly 3 matrices A, B and C, if I take the transpose, see in this case, first matrix was A, second was B, so second and then first. Now here A is first matrix, B second matrix and C is third matrix. So it will change the order. So third matrix, second matrix and then first matrix. This we call reversal law. It is just going to reverse the matrix. Now as I said, no, for addition also, now I'm talking about this one, A plus B plus C, associative. Associative, when we are talking about associative or the addition of matrices, even if I had negative here and here, then also it is going to be A plus or minus B, then plus or minus C. When I write together, the meaning of that is above sign with above, below sign with below. In representing twice, I wrote together. Okay, same thing here also. If it is plus, this should be plus. If it is minus, this should be minus. Okay. So similarly, this also A plus B plus C. If I give again minus here, it can be. I think I wrote the same thing. Now here one more distributive law. So if you see here, then it will be AC plus or minus BC. Similarly, if I got A, B plus or minus C, is the same as AB plus or minus AC. Okay, so again, this is distributive law. Fine. Now let us also try to understand some of the important theorem on symmetric and skew symmetric matrix. So symmetric and skew symmetric matrices. What? If I talk about any square matrix, if A is any square matrix, if A is any square matrix of order n, then first point, what? Addition of the matrix and its transpose is always symmetric, whereas subtraction of a matrix and its transpose is always skew symmetric. And every matrix A can be expressed as sum of symmetric and skew symmetric. This was one of the important 3-marker question which we had. And from this, one more thing we can understand is A plus A transpose symmetric. When I multiply half, again it is what? Symmetric. A minus A transpose is skew symmetric. Again, when I multiply by half is again what is skew symmetric. From here, what we can understand is if A is symmetric matrix, then, okay, wait, if A is a symmetric slash skew symmetric, or than that, no, I'll just write like this since space is not sufficient for a while. What I want to comment, listen. Let us suppose I have got a matrix A, okay. Now this matrix, let us suppose A is symmetric, okay, symmetric matrix. And let us suppose a case where A is skew symmetric matrix, okay. Now in that case, if I multiply the same matrix K, means A by K, it's again what? Symmetric only, where K is any real number. Similarly, for skew symmetric matrix, again let us suppose for this skew symmetric matrix, I multiply scalar K. Again what? Skew symmetric only. So scalar multiple will not change the symmetry or skew symmetry of a given matrix. Okay, so this is all about the properties. One last thing I want to comment here, invertible matrices. With that, entire thing will be done. What is invertible matrices? A square matrix A, I'm saying a square matrix A, so the order should be same. Number of row and column should be same. A square matrix A is said to be invertible if there exists a matrix B such that A into B is equal to B into A is equal to what? Identity. Again, it's commutative. So commutative will be there, but in special cases like this, B is said to be inverse of A. B is inverse of the matrix A or invertible, and we denote B as, see carefully, I said what? B is inverse of A, correct? No. So B is inverse of A, that is, we said what? B is inverse of A. So I write B, is means equal sign, inverse of A, and this is not equal to 1 by A. It is just a notation saying that B is such a matrix. If I multiply with the square matrix A, I get back identity, and this is unique. Okay, every identity, I mean to say every inverse is unique. We cannot have more than one inverse. Okay, we cannot have more than one inverse. And lastly, one more thing is A into B whole inverse is B inverse into A inverse. Same like transpose, the order is getting exchanged. Even the invertible also order will get exchanged. Okay, kindly make a note. Yes, dear students, with this we have completed all the synopsis of the chapter matrices. So this will be regarded as part 1. Whatever I already uploaded, I will just change the thumbnail as part 2, and the remaining problem whichever is there, that will be part 3. Okay, now after this we will go ahead with the chapter determinants. Kindly study well, do well, give you 100%, be dedicated. Okay, don't forget your turning point, April 23rd, 24th is your Kcet exam. So at the earliest we have to complete, and you have to keep a notebook in front of you and write, make a note. Don't be lazy, don't be lying on the bed and then listening. No, you have to sit erect, take the notes, take the all the properties, and whatever the properties I discussed is confined to PUC. There are some additional properties which I have discussed as and how we have solved the problems. Okay, fine. Thank you all. All the best. God bless you. Do well. Give you 100%. Okay. And lastly, do like, share, and subscribe to our YouTube channel, Math Universe with Dr. Naseer Ahmed. Thank you all.